Okay, so in this third and the final step of problem solving, we're going to actually do the details, which means we actually are going to solve. Before that, we're trying to walk up to what method might work. And so now we're going to do the detailed algebra, for example. Okay, so as we keep saying that we're going to do this solution by analogy. So here is my control volume. Control volume here, that is the spherical shell over which we're going to do the energy balance. Heat is conducted in and then conducted out. So for energy balance, we know what we need. We need the conservation of energy. So in minus out, generation equal to change in storage. We're going to apply this on this control volume. Okay, so let's look at all the separate terms. So let's call Q R double prime is equal to flux at radius R. Okay, so if that is the flux, then flux multiplied by the surface area at radius r, that's here, this surface area, the unit for this flux is what? It's in watts per meter square. So if I multiply that watts per meter square by meter square, then I get watts times second. The conduction over time delta T is going to give me joules. So the unit for this entire thing is joules. And this is what is coming in. So this is joules in. And in exactly the same analogous way, the flux at R plus delta R is Q double prime R plus delta R symbolically. And so that's here, that's the flux or heat flow per unit area times the area here. So the area here, because the radius here is R plus delta R, so the surface area is 4 pi R plus delta R square times delta T. The same way, just like the last one, this is also in joules. Okay. Now, how much heat is generated inside this during the time delta T? So that would be Q, the rate of heat generation. So Q here is the heat generation per unit volume times the volume of this shell. So the volume of this shell is 4 pi r squared delta r. So this is watts per meter cube times meter cube. So notice this is still in watts. So there is a mistake here. We should add delta T, which is in seconds. So this total thing is the amount of heat in joules, because this meter cubes cancel, so we have watts. Watts times second is joules. So the joules that is generated is equal to the change in storage. So this is my generation term, and this is my out term. And then the change in storage. So because of energy going in, out, generation, we're going to have change in temperature of that. And let's say the change in temperature over time delta T is delta capital T. Okay, so mass of this volume of this shell times specific heat times delta T is the change in storage. Okay, so mass is volume, which is 4 pi r squared delta r. Because it's a thin shell, the volume is 4 pi r squared times delta r. Volume times density is mass. Mass times specific heat is the change in storage. So this is exactly what we did in case of radial cylindrical coordinate system and in Cartesian coordinate system. Now we divide throughout by r square delta r delta t. If I divide throughout by this quantity, divide by this. Okay, then we get this one, so you can see r squared delta r in the denominator plus this. Now you notice that this part of it you can see that it's a function at r plus delta r minus the same thing at r. So where it's r plus delta r, it's r here. Likewise for q. So function at r plus delta r, this one, and function at r divided by uh, delta r, and so this part of it is when I let delta r go to 0, it becomes the derivative, and the r square simply stays there, this one. Okay, and plus q, and then rho cp, that stays the same, and as we make delta t go to 0, then this becomes the derivative. So this equation now has no knowledge of the Fourier's law. We just did an energy balance, that's all. We still have this flux sitting out here that we have to do something about. So we're nearing the end. We simply have to plug in for this QR in the r direction. Q r double prime, or the flux, is minus k del t del r. This is my Fourier's law. This is my Fourier's law, and I simply need to substitute that to get this one. You notice everything else is the same, and then the signs cancel each other to get this term here, and q stays the same, and the right hand side stays the same. So all together now we have the heat equation with only the r direction. So we have dropped out theta, and phi has been dropped out. If we kept them, we'll get more terms. We also have dropped out no flow. So the velocities convection part has been dropped out, just to keep life easier. One thing is we still have k sitting inside. We can bring k outside only if we assume k to be constant. So for constant k, then k can come out, and we have this equation. If you want the analogy, uh, with Cartesian, it is k del square t del x square plus q is equal to rho cp del t del t. Okay, so you can see how analogous the two equations are.